Hi there guys, today we're going to have a look at how to transform functions. So I've got a pretty gnarly looking function here, and we're going to use the same function for all of the different types of transformations. I probably could have made it easier for myself, but let's go ahead and do this. So let's sketch this graph. So you should know now the roots are going to be 1, 3, and -2. And if you put the x coordinates equal to 0, we can have -3 times -1, which is 3, times 2 is 6. So it's actually going to cross up here at 6. Let's just make a sketch of this. Okay, so it's cubic, so we know it's going to start, because it's x cubed, it's going to start in this bottom left hand quadrant. So it's going to come up, down through here, and then like so. Now it's not the best graph, but actually I'm just going to pause the video, you won't notice, and I'm just going to repeat this for all of my different questions so I don't have to keep drawing this every single time. Okay, so here we go. I've just literally repeated that graph twice. Now you need to know what this means. You need to look at these and say, I know exactly what these transformations are. Now with most transformations, I like to go back to my trig graphs. So let's take this one for example. Throughout this video I'm going to be drawing the sine of x. So you should know it goes something like that. That's 1, this point is -1, and it completes its full cycle at 360. Now, so basically what that means, for this one, the x values will go from 360 to 0 for one complete cycle. You know it goes on forever and ever. But if we had something like sine x minus 90, then we could solve this using our compound inequality knowledge. Like so. So if we add 90 to both sides just to get x on its own, we would have 450 and 90. Which means this new graph would actually start here and actually end, say, about there. Like so, and you can see that the green graph has moved right 90 degrees. So x minus 90 like this means we're actually moving it right. So when I'm not one for remembering rules. This is a pretty easy one to remember, but this means we're actually going to move right 2, and this one means therefore we're going to move left 1. So we basically have to take all these coordinates and move them right 2. So this one is going to be there. This one is then going to go there. We're going to have to make this a bit longer to 5. And 0, 6 is going to become 2, 6. So we're just going to draw exactly the same graph again, making a note that it's probably going to come up to about here. Down through there. And there you go. That's it. So whether you draw it on the same graph as the original, or you just, what we need to see is the intersection points. We need to see stuff like this. We need to see the points that you're trying to map. This has to go left 1, so that's going to go to -3. We're going to go to this point here, bearing in mind this point is also coming over. That's going to hit 0, and this one's going to hit 2. So here we go. So you can see it's moved left 1. Okay, that's that type of transformation. If it's outside of the bracket, +2 or -2, this is like the y-intercept knowledge. You should know that this means it's moving similar to the y-intercept, so it's going to be the one going up and down. We have a left and right transformation, and if you know that one, the other one is up and down. So that's always going to happen with the plus and minuses that you see. So this means up 2, and this one means down 1. Just like on a y-intercept, that would be a +2, and that would be down 1. So this one's going to go to 4. This point here is going to be down here. Let's put it all on the same line. If it helps you, you can draw like a dotted line, like 2 down, so then it helps. So here we go. And there we have it. And it's worth putting the coordinates on. Well, you have to. So that's going to be -2. Oops. That's going to be -2, -2. This one's going to be 1, -2. And this point here, it's that point there. So it's 3 -2. And you can put that as a 4, like so. Alright, simple as that. Oh, I moved it the wrong way. Alright, for this, just imagine that was a -2. So I really don't want to make this again. So just so I can show you, let's make this one a +1. So this is actually going to go up 1. So this one's going to go to 7. This one's going to go to 1. So that point there is going to be -2, 1. This point here is going to be 1, 1. And this point here, let's put an X, is going to be 3, 1. Just put that there to help me. Okay, so it's just moving it one place up. I do apologise about that, but it's a hell of a lot easier than remaking the whole video. Okay, so it starts to get a bit trickier now. So when I see, I said about pluses and minuses, but that's with a number attached to it. When it's like this, I always start with this one, and I think of the graph y equals x squared. And then I think of the graph where if there's a minus in front of it, just like this function has, that just reflects it clearly in the x-axis. So it means that every single one of these points is going to be reflected in the x-axis. So this one here, 6, that's going to be here at -6. The roots, you'll see, will stay the same. Now they're the only coordinates we know for definite, but let's just roughly map out where these points are going to go. So we're going to come down here, up through there, and down. So if this is a reflection in the x-axis, this must be a reflection in the y-axis, which means that so this -2 is now going to be at 2. This 1 is now going to be at -1, and this 3 is going to be at -3. This point here is going to be roughly there. Well, the scale's a bit dodgy, so this is just over 2, so this has to be just over 2. So this one's going to be way over here, and this point's going to be here. Okay. So let's try and draw this. This isn't easy. I actually struggle to draw these. So it's going to come up, like so. This point is going to be exactly the same because it's on the y-axis. We're going to come down and under. Right, I really do apologise. It's not the best effort, but you need to understand what I'm doing. It's much easier with pen and paper. But every single one of these points is being reflected. So that should be there, the same distance here. My scale's all over the place, so it's not the best. But that's it. Reflection in the x-axis, reflection in the y-axis. Just remember one, or work out one, and then just do the opposite for the other one. Okay, now the hardest type. So I'm going to go back to my sine graphs. I'm just going to put a page in to help me explain this. So here's sine of x again. Alright, and you need to remember what sine of 2x looks like. And it's this. Basically, it repeats 2 cycles in the 360. So this one is sine 2x. Now the reason it's important to do this, because what you can do is work out what's happening to the x and y coordinates. So you should know this one is 90 and 1. You should know, therefore, if I half it, because I'm fitting 2 of them in the same time, it's going to be squished in half, it's 45 and 1. So the x coordinates are actually dividing by whatever that number is there, whatever this is. It's being divided by that. So if you wanted to write a general formula, the x coordinates are divided by a. And the y coordinates, you'll see, they're both 1. So they're the same. So we're going to divide it by whatever that number is. Alright? So let's go back. So here we know let's write our coordinates down. In fact, just pop this down a tad. Maybe one more. We've got the coordinates -2, 0, 0, 6, 1, 0, and 3, 0. I'll just make the screen a tad bigger. Now, we know the x coordinates are going to be halved and the y coordinates are going to be the same. So this coordinate is going to go to here. 0 is going to stay the same. That's going to be a half 0. And this one's going to be 1.5 0. So -1, 0, 0, 6, that's the same. Half 0, so that's there. And 1.5, so let's say that's 2, let's put it there. Okay, now pay attention because the y coordinates aren't going to change. So this value here, let me just draw a dotted line across here. That's going to be the same because this point here, which we don't know the coordinate, but the y value will stay the same. The same for this. This point here is going to come down to the same level. So change color to green just to help you see this. So it's going to come up, hit that point, but down, hit that point, and then back up again. So you can see it's squishing, but the heights are the same. And you can appreciate that hopefully from here as well. The heights were the same. Okay, so this one we're going to divide by this. So dividing by a half is the same as doubling, because how many halves fit in 2, for example? That's 4. 2 doubled was 4. So these coordinates that we had before, I just rewrite them again, are actually going to be doubled this time. So -2, 0, 0, 6, 1, 0, and 3, 0. Oops, didn't mean to do that. So that's going to become -4, 0. This one is going to stay the same. This one's going to be -2, 0. This one's going to be 6, 0. Right, so let's plot these. We're going to have -4. We're going to have... Oh, don't know why I changed that to a minus. Do apologise. That's going to be 2. This one is going to be 6. Let's put it all right over there. And remember, the y's are not going to change. Right, it has to hit this point. And we've also got the same coordinate here. So it's going to come up. It's going to hit there, come down, through here, hit this point, and then go past. So you can see it's, stretched out, if you like. So it's very hard to remember, but the sine graphs are going to be your friends with these. And the same with this one. If we insert another page and draw a sine graph again, let's make this sine x here. That's 1 and that's -1. If I was to draw 2 sine x, that would actually do this. Go up to 2 and down to -2. So if we map these coordinates again, we're going to have 91 and 92. So this time the x's are staying the same, but the y's are being doubled, or times them by a if you wanted to put like a general formula to it. Okay, let's apply that. Oh, I haven't drawn these graphs. Hang on, I'm just going to pause it and